All right, good morning, folks. Let's go ahead and let's pick up where we left off with yesterday. I'd like to try to get done with the discussion of solids today and try, if we can, to get into the discussion of phase changes and then finish up this chapter. Okay. All right, so we left off yesterday with the discussion of boiling, and we defined boiling not only in terms of what we can observe, but also in terms of the pressure. And I think that's a more appropriate and more accurate description of what boiling is. Okay? So we saw that boiling, what we can observe with boiling is that we see the bubbles. Those bubbles we were able to show yesterday are the vapors of the liquid themselves. And we see those bubbles because we increase the kinetic energy by increasing the temperature, increasing the kinetic energy of those particles to the point where we were not only getting vaporization occurring at the surface, which still does happen. We said that evaporation does occur even when evaporation occurs when the liquid is boiling. So we not only get the vaporization occurring at the surface, but now we're also getting the particles to vaporize underneath the surface as well. And so those bubbles that we see represent then the vapor particles of the liquid. So these are not air bubbles, these are bubbles that form from the vapor of the liquid. And the reason why is because those particles now underneath the surface are able to get enough kinetic energy where they also break those attractions that they have for their neighbors, and then they become vapor particles as well. Okay. All right. So we said then from that we started to examine this graph here, because I did give you so at the end of the period, towards the end of the period yesterday, we talked about how a boiling liquid is a liquid that is exerting a vapor pressure that is equal to the external pressure, the pressure that is exerted by the air outside of it. And so that's what you got to make sure you understand, that we're comparing two things when we are defining boiling in terms of its vapor pressure and the atmospheric pressure. We're looking at two different pressures. The pressure exerted by the atmosphere, and we already talked about that way back when we were discussing gases. Remember, the atmospheric pressure is a result of the air particles around us. So the the air is made up of a mixture of gases, oxygen, nitrogen, carbon dioxide, water particles even. Okay, so with that said, then we have the air around us. Those particles are gas particles, and those gas particles collide with everything around it, and that's what creates pressure. And then we saw then that if we can imagine the air pressure as being a column of air pushing down on everything underneath it, then that is what we refer to as atmospheric pressure. Okay? And so here at sea level, towards California, wherever we are at here at sea level, the normal atmospheric pressure is about 101.3 kilopascals, or 1 atmosphere, 760 millimeters of mercury. That's the pressure exerted by the air as it pushes down on us. And we also saw then that as we move up in elevation, as we go higher and higher in elevation, as we move up in altitude, we see then that the atmospheric pressure is going to decrease. Okay? So that's atmospheric pressure. But we saw then that liquids also exert a pressure. They exert a pressure by evaporating, and they have what's called a vapor pressure. Okay? And so when we talk about, and that vapor pressure results from the evaporation of a liquid as it moves into the gaseous state. Okay? And so we saw then yesterday, and we defined then yesterday then that the boiling point. The boiling point then is what we can observe at the boiling point are those bubbles, so make sure you keep that in mind. So when a liquid starts to bubble the way that we see a liquid boil, okay, when a liquid is boiling, think about water when you heat it up, okay, when it starts to boil vigorously, that is when the liquid is bubbling. But that is also when that particular liquid, and we're going to continue with water, that at that point then, that liquid is exerting a vapor pressure that is equal to the atmospheric pressure. Okay? All right, so with that said then, what we did is we took a look at this graph yesterday. Okay, so we took a look at this graph yesterday, and we were able to answer some questions about it, and I want to continue on with it. Okay, so we saw then that at each one of these temperatures here, and I'm going to trace the line again, that with each one of these temperatures here, and I'm going to go ahead and here, at each one of these temperatures then, at about negative 23 degrees Celsius, we see then that at this point here, at that temperature, the pressure, the vapor pressure of the dimethyl ether is about 760. So we saw that as well. So I'm just going to go ahead and highlight that really quickly. So roughly at this point here, and so we're just looking at the pressure. Let's go ahead and draw the line right there. So at this point here, at this temperature here, the dimethyl ether at this temperature, it has a vapor pressure of about 760, and then in this case, it'll be torr. Okay, and so the pressure exerted by dimethyl ether at negative 23 degrees Celsius is 760. Okay. And so I asked you about water. So let's go ahead and take a look at water. At 100 degrees Celsius, let's go ahead and trace the line up right here. So this is 100 degrees Celsius. Let's go ahead and take a look at that. That would be the pressure exerted by water. Water, and trace it back, and we see then that the pressure exerted by water is also at this temperature is also 760 torr. Okay, so this is the vapor pressure exerted by water. This is the vapor pressure exerted by dimethyl ether. It's the same vapor pressure. Okay? And so we notice then at both these temperatures, then each liquid is exerting that exact same vapor pressure. Okay, so this is the vapor pressure exerted by water. And if you look in the box here, what I've told you then is that atmospheric pressure at this point, that atmospheric pressure at sea level, and we're going to assume that we're taking these measurements at sea level, is 760 torr. Okay? So at this point, then let's consider what we have here. At this point, then we'll call this atmospheric pressure. Okay, so atmospheric pressure is 760 torr. Okay, so this is atmospheric pressure, the atmospheric pressure. Okay. And at this temperature, we see then that water is exerting a pressure. At this temperature, water is exerting a vapor pressure, and so we'll call this vapor pressure. Pressure of 760 torr. Okay, and so what do we notice about this? At this temperature here, then, at this temperature, the two pressures are equal. Okay, if the two pressures are equal at this temperature, and that's what I asked you yesterday to consider, folks, at the end. Okay, if what's the significance of this temperature then? Well, first of all, we know from just from our experience that this is the boiling point. And the boiling point, remember, we define then as the temperature at which the vapor pressure equals the atmospheric pressure. So we've just increased the temperature up to the water's boiling point. And at this point here, this is when we'll get the fastest rate of vaporization for water. Okay. This then represents the fastest rate of vaporization for dimethyl ether. This is when each one is at the boiling point of any liquid. That's when you get the greatest vaporization, the greatest rate. That's how rate meaning how fast a liquid will vaporize. Okay. Just imagine this: when you evaporate a liquid, it vaporizes very slowly. That's why you'll see the liquid level drop, but it's indiscernible for some liquids, a drop in liquid level. However, when you get to boil, you can see that liquid level drop at a fairly higher rate. Okay, so at the boiling point, the vapor pressure equals the atmospheric pressure. So at this temperature, you get that, but you'll also get the fastest rate of vaporization as well. And so make sure you keep that in mind. And that's it. Okay, so that's how we then can define the boiling point for any liquid. So a boiling point, folks, is a temperature. Okay? It's a temperature at which we see the bubbles form in the liquid. And at that point, then we know that the vapor pressure is equal to the atmospheric pressure. Okay? And if we can use that to our advantage, we can at that point then determine the vapor pressure of the liquid without having to measure anything. Okay? Because we know, if we know what the atmospheric pressure is, we'll know what the vapor pressure is. Okay? All right, very good. Let's go ahead then. Let me ask you a few questions about this. Okay, and let's take a look at this graph here. So again, we have vapor pressure. This time the vapor pressure is in millimeters of mercury, so we're graphing vapor pressure versus temperature again for three liquids. Ether, different liquids now, ether, ethanol, and water. Okay, so we got our three liquids here. Let's answer some questions about this graph here. based on what we know so far. Okay, so I want you to, let's get out your piece of paper, and let's answer these, and then we'll go over them together. Okay, let's answer the first one. Okay? What is the boiling point of ether? Okay, what is the boiling point of ether? So go ahead, write your answer in there, okay? And then unpause the video, and then we will talk about it. Okay, so what is the boiling point of ether? Okay. All right. Now, let's go ahead and let's consider this. Remember, we said then the boiling point is the temperature at which the liquid's vapor pressure is equal to the atmospheric pressure. Okay? And so we were saying then, here's the temperature right here. We're talking about the temperature of 760 millimeters of mercury. Remember, that's equal to 1 atmosphere. Okay, so what is the boiling point? And so we're looking for a temperature. We're looking for a temperature for the ether here when it has a vapor pressure of 760. So let's go ahead and let's trace what we have here. Okay, so let's go ahead. This is roughly about 760 here. So we'll trace over. So there's ether. Okay, so there's ether. It has a vapor pressure of 760. Then what we do is we just go down from this point. We go down to the x-axis, and we see then right there the boiling point of ether then is around what, 39 degrees Celsius. So we can go ahead and write that down. So the boiling point, abbreviated BP, of dimethyl ether, of ether, is going to be about 39 degrees Celsius. Okay, so there it is. That's our answer. Okay, very good. Let's go ahead and let's do another one. Okay. What is the pressure of ethanol at 40 degrees Celsius? Okay, so take about 30 seconds, answer that question, and then let's come up with the answer together. Okay, so the pressure of ethanol at 40 degrees Celsius. Okay, let's go ahead and let's take a look at ethanol, folks. So this time though, what we're going to do is we're going to, if we're given the pressure at 40 degrees Celsius, okay, let's go and find ethanol. Ethanol is the blue curve here. Let's go to 40 degrees Celsius right here. So this 40, we'll trace our line up to the graph. Okay, so at that point right there. And then we will move over and trace it back to the y-axis. Okay, and so at that point, then that's about what, 100 and let's say 180 millimeters of mercury. So the pressure of ethanol at 40 degrees Celsius is the vapor pressure. Let's go ahead and write this down. Vapor pressure of ethanol is going to be equal to about 100. Let's say 100 and that's a little bit more than about 150 millimeters of mercury. Okay, so that would be the vapor pressure. So let me ask you this question really quickly, and you can just answer it real quickly in your head. Is this the boiling point of ethanol? Is this the boiling point of ethanol? And the answer there is no. Because remember, the boiling point of ethanol has to be then the temperature at which this vapor pressure is equal to the atmospheric pressure. We can say this right now, folks. Let's go ahead and put that up. So right now, we can assume then the atmospheric pressure at which we are going to take all of these measurements is about 1 atmosphere, okay? About 1 atmosphere, or 7, since we have millimeters of mercury here, 760 millimeters of mercury. Okay, so at 40 degrees Celsius, the vapor pressure exerted by ethanol is not even close to 760. Okay, so it does not boil. So you can imagine at this temperature here, which is a little bit above room temperature, at this temperature here, ethanol will not boil. You won't see the water, you won't see ethanol boiling. However, with ether though, real close to 40, at this point here, you will see ether bubble. You'll see. And this is not it's warmer. Okay, it's on a warm day. You can imagine this being a warm day. You'll start seeing ether start to boil, just like water. When you see it boiling with the bubbles, you'll see ether bubble at 40 degrees Celsius here. But ethanol will not. Okay? And so there's a difference, and that's how. And we'll get to this in just a moment. That's how we can also use boiling point as a property that we can use to distinguish different liquids. Okay? So we saw then how we can use vapor pressure to distinguish different liquids and identify them. That's a little bit more difficult to use. However, we can use boiling point. We can definitely use boiling point in order to identify different liquids. That's a little bit easier to do. Okay? All right, very good. Let's do one more question before we finish up with this graph here, this page here. Okay. The question then is, what would you need? What would the atmospheric pressure be? Okay, for water to boil at 80 degrees Celsius. Okay? All right, so go ahead and answer that question. So the question is about atmospheric pressure now, not about vapor pressure. What's the question is about atmospheric pressure. Go ahead then and take about 30 seconds to answer that question. Okay. All right, let's go ahead and 80 degrees Celsius. Okay, so first of all, if we want this to boil, okay, we want this to boil, we want to make sure then that we are looking at the temperature here of 80 degrees Celsius. So let's go ahead and let's find 80 degrees Celsius, okay, on this graph here. So we'll start out at 80 degrees Celsius, okay, and we're going to trace our line up to that point right there. There it is. So that's where the this graph here meets 80 degrees Celsius. And then we're going to go ahead and trace the line over to the y-axis. Okay, so at this point here, let's go ahead and write this down, folks. At this point here, the pressure at 80 degrees Celsius, the vapor pressure exerted by the water then is about what? 380 millimeters of mercury. Okay, so this would be, from the table here, from our graph here, this would be the vapor pressure of water at 80 degrees Celsius. So if we saw this here, if we had, so 80 degrees Celsius, and if we had this particular water here at sea level, and again, atmospheric pressure at sea level is 1 atmosphere, we wouldn't see the water boil. We would not see the bubbling occur. This question is asking us then, and let's go ahead and consider this here. This question is asking us about boiling. That is, how can we get water to boil at 80 degrees Celsius? Well, we think, when we stop to ourselves and we think, well, water doesn't boil at 80 degrees Celsius. We just saw on the previous slide that water boils at 100 degrees Celsius. That is, at 100 degrees Celsius, when you crank up the temperature to 100 degrees Celsius, that's when you'll see the bubbles, you'll see the vigorous bubbling. And so the question here is asking us, can we get water to do that at 80 degrees Celsius? Is it possible to get water to boil at 80 degrees Celsius? Well, the answer there is no, if we are trying to do this at 1 atmosphere, at sea level atmosphere. Okay. However, is it possible to reduce atmospheric pressure? Is it possible to make that pressure less? Because if we can reduce the atmospheric pressure from 760 millimeters of mercury down to 380 millimeters of mercury, okay, then you could boil. And so therefore the answer then, in order to get water to boil at 80 degrees Celsius at a lower temperature, we would have to have the atmospheric pressure be equal to 380 millimeters of mercury. Because remember, we define boiling as the temperature at which the atmospheric pressure equals the vapor pressure. So we can't change the vapor pressure. Obviously, we can at 80 degrees Celsius. That's the vapor pressure that that water is going to exert. If we want that water to boil at that temperature, then we just reduce the atmospheric pressure. And so you ask yourself, how in the world can we reduce atmospheric pressure? Is that even possible? And folks, the answer is absolutely yes. Okay, we can reduce the atmospheric pressure, and if we do so, we can get water to boil at a cooler temperature. Now, again, it's possible to get water to boil, and unfortunately, this is an experiment that I used to do in class. Okay, I would get out my bell chamber. Okay, I would get out my vacuum chamber. Okay, I put a beaker of water inside that vacuum chamber. I turn on the vacuum pump, and I start pulling air out of that vacuum chamber. And as we start pulling air out of the vacuum chamber, then we know then that the atmospheric pressure inside that chamber is going to be less and less. Why? There are less and less particles. There are less and less particles inside that chamber, and so we have less pressure inside it. And sure enough, as soon as we drop the pressure below a certain point, we see, and I'm not heating up the water at all, folks. I'm not heating the water. I took water out of the tap at room temperature, dropped it into the vacuum chamber, and at a certain point, and I'll try to find a video to show you this, but like I said, I would demonstrate this in class. At a certain point, the water, you start seeing that bubbling. You start to see the bubbling water, and you observe that, and that's water boiling. and then I shut off the vacuum chamber. I open up the let air back in, and then I take the water out, and the water is still at room temperature. It's not hot, but it did boil. Okay, and so the question then is, I did that with the vacuum chamber. Okay, we don't live in a vacuum chamber. So my question to you here is this, and I want to finish up with this. Using this graph here, okay, what does this graph tell us about altitude, okay, altitude versus boiling? Okay, so make sure you add, so let's, okay, I'm running a little low on time here. So let's do this. Answer this question for tomorrow. You answer this question for tomorrow, and make sure you support your question, your answer with the information from the graph. Okay, so answer the question. Again, the question is, what does this graph tell us about the boiling point? Okay, the boiling temperature and altitude. Okay, so this is pressure. This is pressure listed for us. Okay, so I'll just go ahead and write this here. This is pressure measured in millibar. And millibar is a pressure unit used by the weather people, by the meteorologists to measure atmospheric pressure. So this is atmospheric pressure on the measured on the y-axis. So this is atmospheric pressure. This is no longer vapor pressure. This is atmospheric pressure. This is atmospheric pressure measured along the y, okay, and temperature measured along the x. Okay, so what does this particular graph tell us about the boiling point of this liquid, at different atmospheric pressures? Okay, so go ahead and make sure you answer the question, okay, and we will pick up with this discussion tomorrow. Okay, have a good day, folks, and I will see you tomorrow. If not, again, I will be available today, office hours. And then come by and see me if you have any questions. Okay? If not, I will see you tomorrow.